Okay, so welcome to the second session of the day. Our next speaker is Minjae Cho, and he is going to talk about a non-worldsheet description of string backgrounds.
Thank you very much. Can you hear me well? Sounds good. Actually, as you can notice, there's a typo in the title, which I found only this morning. It should be string backgrounds instead of strings backgrounds. Well, I have a justification for this. It just reflects how much I'm excited for Strings 2024. So I wish to first start by thanking the organizers for organizing this wonderful conference and for giving me the opportunity to speak. So I'm going to tell you about a non-worldsheet description of string backgrounds. This is based on my current work in progress and also past works with my wonderful collaborators, Monkey Kim, Nathan Eggman, Scott Collier, and Sheehan. So let me start by asking the following question. How do we describe string backgrounds and physics around them? If there's an easy worldsheet CFT description, good, we can do ordinary string perturbation theory. But unfortunately, such a description is not always known explicitly. And in the NSR formalism, for example, we lack such a description for the cases where you have Ramon fluxes in the background, which unfortunately includes most of ADS and flux compactifications, even though alternative formalisms may be present. In contrast, low-energy Sugra description provides the Einstein equation, and once you find the solution to it, we interpret it as the string background, but it comes with a limitation that observables beyond the protected quantities are very hard to access. So it'll be great if there's a stringy version of Sugra. And string field theory, in short SFT, comes close at least conceptually. And I think probably some people in the audience might think that it's a humongous, gigantic construction, which is very scary. But my goal today is to convince you that it can be actually useful in practice. Okay. So before jumping into the details, let me give you some broad picture about what string field theory is like as of today. By now, I think it's fair to say that string field theory is a well-established framework for perturbative strings in NSR formalism, mainly thanks to Ashok Sen, Barton Zuibach, and many other collaborators. And here are some helpful references. And the upshot is that it's now waiting for interesting applications. But it comes with a limitation. First of all, it requires a good starting point described by an exact worldsheet CFT. Let's call such a background T0. So this is our starting point. Once you plug this into SFT machinery, it's going to produce a path integral. So the question is, what is this path integral? It's an integral over this field phi, which are called string fields. Okay? The worldsheet CFT Hilbert space of T0 is going to provide a space of string fields. And these string fields phi are space-time fields, and this action in the path integral is space-time action, rather than the worldsheet action. So string field theory really sticks to the space-time picture. This action is perturbative in G string and phi, at least in the presence of dynamical closed strings. And its terms can be computed using the worldsheet CFT correlators of T0 on Riemann surfaces. If one is interested in computing observables up to specific order in G string and phi, then terms in the action beyond some finite orders are not relevant. And the action provides the Feynman rules we can use to systematically compute physical quantities order by order. So you might ask, what can we do with it? For most of the interesting applications, I will refer you to Ted and Shi's talk. For this talk, the focus will be on how we describe and study string backgrounds. The idea is actually simple. We have something that we want to interpret as the space-time action. So by varying it, we are going to obtain equations of motions. And let's say we find a solution phi star. Just as solutions to the Einstein equation describe GR backgrounds around which we can study the physics, this phi star stands for a string background. But due to the limitation of the current formulation of string field theory, this phi star can best be obtained as some expansion around the original background T0, which nonetheless may converge. Within this limitation, there are still interesting backgrounds which we can study, such as ADS5, where we take its inverse radius as the expansion parameter around the flat background. Say we found a solution. Now we are going to expand the action around that solution. We are going to call this new action S star. Its linear equations of motions gives rise to the free string spectrum of this new background phi star, and its Feynman rules can be used to obtain stringy observables of this new background. And let me emphasize again, this S star provides a space-time description of strings in the background phi star. And it still computes stringy physics. So now let's get into more details. How do we define the string fields? So we started with an user worldsheet CFT, say its Hilbert space given by H naught. We are going to focus on states satisfying some technical conditions. We are going to expand general state, which is not BRST closed and thus off shell, into some basis. And there's going to be the coefficients sitting in this expansion. And these coefficients are string fields. For the superstrings, there's going to be also restrictions on the picture number. But the important point is that Ramon-Ramon fields are also part of the string fields. So how do we construct the action functional of these string fields? For the kinetic term, we expect that the corresponding variation should produce free equations of motions, which is given by BRST closeness condition. So it's actually straightforward to guess what the kinetic term should be like, and it's written here. And by inverting it, you can also get the corresponding propagator, which in single gauge looks like this B0 plus over L0 plus. What about the vertices? You can compute them in a way very similar to the usual on-shell amplitude computation, meaning that you take CFT correlator and integrate over the moduli space of the Riemann surface. But there are actually some key differences. The first is that we are going to integrate over only a part of the moduli space called vertex region. This is such that Feynman diagrams built by propagators and vertices cover the moduli space exactly once. Also, we need to specify the local charts around the punctures because the insertions are no longer on-shell. But it was shown that different choices of local charts are related via field redefinition so that they do not affect the on-shell quantities. In superstring, you also have to specify the PCO locations, but for the interest of time, I'm going to omit the discussion. So here's an example of sphere 3-point vertex. So you can see this dot. This stands for the zero-dimensional moduli space of three-puncture Riemann sphere. And over that, we have this infinite dimensional fiber, which stands for the choice of local charts. You can make one choice, you can make another choice. They are related via field redefinition. Say we made a choice, and we are going to draw the corresponding Feynman diagram like this. So here's an example. Let's denote the sphere global coordinate as z around the origin. We are going to take the local chart W naught, which is unit disk, to be like this. Z equals to r times W naught for some positive r. And we can do similar thing for z equals 1 and infinity. And different r's correspond to different vertices. Let's say we made a choice. Then what we are going to do is that we are going to basically evaluate the sphere 3-point correlator in this specific local chart choice. Okay? And that's what we are going to denote with this double bracket. And that's going to be the sphere cubic vertex term in this action, and which of course depends on the choice of r, and it's a functional of string fields. If you have two of such cubic vertices and a propagator, you can draw a Feynman diagram like this. And at the level of the Riemann surface, what's happening is that you have this plumbing construction. So you are identifying the local charts of the left part and the right part using plumbing parameter Q. The end result of this is that you produce two real parameter family of four-puncture Riemann sphere equipped with local charts around the four punctures induced from the cubic vertex. So this is roughly what it looks like. Again, we have this four-puncture Riemann sphere moduli space labeled by cross ratio. And in some neighborhood of 0, 1, and infinity, we can cover the corresponding moduli space using this plumbing construction, basically Feynman diagrams with the propagator. But it will turn out that these blue regions are not going to be covered by this construction. And this is exactly where we are going to define 4-point vertex. So over this blue region, say we make some local chart choice. We are going to call it 4-point vertex. But we have to make sure that this chain is actually boundaryless. There's no boundary component. And this guarantees the null states decoupled from the on-shell amplitudes, and thus is intimately related to the gauge invariance. So this is how it's like. So we integrate only over the vertex region of the four-puncture Riemann sphere moduli space, and we evaluate the correlators using the local chart choice that we made. And this is the sphere quartic term present in the action. And basically, one can repeat this exercise of plumbing, filling in the missing pieces by vertices, and so on to higher points and genus. And this no boundary condition to all orders is something called geometric master equation, whose solutions are known. And it simply implies that the action S sub q, so constructed, solves something called quantum BV master equation, is a technical name for this action being consistent in the sense of gauge invariance. So this is the action that we have. By collecting the 1PI diagrams, we can obtain 1PI effective action, and the corresponding vertices, 1PI vertices, are denoted with single bracket. So we have the action, we write down the equations of motions by varying the action, and this is what we obtain. Here, this square bracket is something called string bracket, defined in this manner, and it's nothing but the variation of the 1PI vertex. So the question is how to find solution to this equation. We are going to find the solution in some perturbative expansion. Okay? So we are going to take this type of series expansion ansatz. So mu is the series expansion parameter, and uk corresponds to the kth order part of your solution. So we plug this into the equations of motion and solve order by order in mu. At the first order, we are just going to end up with the free equations of motions, and we choose which on-shell vertex operator we want to turn on at the first order. And at the second order, there's going to be source term coming from, roughly speaking, this OPE of U1 against itself. Okay? And then we have to solve for this U2. So how do we solve it? We are going to split the equation into massless and massive sector. We introduce projector called P0. It projects to L0 plus nilpotent sector. And 1 minus P0 sector is where we can invert the BRC charge. And we are going to choose Siegel gauge for that. Then this part is basically the massive part solution for the background, for the equations of motions. And this W2 is now responsive for the massless part. It survives this P0 projection, and it should solve this equation. Okay? Of course, if the right-hand side of this equation is not BRC exact, we cannot solve the equation, and this actually corresponds to the possibility of massless tadpoles. So say we found a solution, a background solution. Now we want to do physics around it. So this is the action expanded around this solution, and again, it describes the physics around the new vacuum V star. By varying the quadratic term of this new action, we are going to obtain linear equations of motions. Okay? And it actually looks like this, where this k, as you can see here, roughly corresponds to inserting arbitrary number of the background solution. So it's roughly similar to the conformal perturbation theory, if you wish. And this combination, Q plus K, we are going to call it Q hat B. And based on the fact that phi star is a solution, you can show that it's nilpotent. So free string spectrum of the new background phi star is given by this Q hat B cohomology, which one can solve order by order in mu. Okay? So now let's consider some explicit examples. We are going to start with ADS 5 cross S5. We are going to reverse engineer the statement that ADS at large radius is flat. So we start with flat background, and going to construct the ADS order by order in mu, which is the expansion parameter, which we identify as the inverse radius. At the first order, we are going to turn on 5-form flux, and this is the on-shell vertex operator for 5-form flux. At the second order, this is the equation which I already displayed to you, but now you can explicitly evaluate this bracket, and straightforward exercise shows that this is the result. And now we want to solve for this W2. It's, again, a straightforward exercise to the CFT exercise to show that the answer is given by this expression. And notice that this part is the usual graviton vertex operator. And this number, multiplying it, G2, which is written here, is nothing but the second order part of the ADS 5 cross S5 metric expanded in large radius, as expected. We can also solve for the spectrum using the linear equation of motions, as I already explained. Let's consider axion field as an example. And here, this F alpha beta is nothing but the one-form field strength. And solution is given by the following form. So you plug this into the linear equation of motions and read out what these guys should satisfy. At the zeroth order is the usual derivative of the axion scalar. At the second order, there's going to be correction to this axion. And this is actually required to satisfy this equation once you use the linear equations of motions. And it's actually straightforward to notice that this is nothing but the Laplace equation in ADS 5 cross S5 for massless scalar expanded to the second order in the large radius, as expected again. Let's consider the next example, which is ADS 3. In this case, we can actually accommodate a mixture of NS and Raman fluxes. And this Q stands for the mixture. And when this Q is 1, we have pure NS background with exact worldsheet CFT description, which is given by this WZW model. We take this as our starting point, T0. And now we are going to turn on F3 to consider mixed flux. And at the first order, this is the unsure vertex operator for F3. At the second order, you can show that the string bracket does not produce any P0 plus sector. So this is the complete answer to second order. Now that we have background solution, let's study the spectrum. We can study the spectrum of something called pulsating string. It's semi-classically a string which pulsates around the center of ADS like this. At the pure NS point, this is the corresponding vertex operator. So here we have J0, which is SL2 quantum number for discrete wrap, J prime for SU2 quantum number, and N is the oscillator number, where this VSL and VSU are the usual current primaries. And for this pure NS-NS case, the unshell condition leads to this dispersion relation. And the question we are going to ask is, as we turn on three-form flux, F3, how this dispersion relation is going to change. And this corresponds to change in ADS3 mass and energy. At the first order, you can show that there's nothing non-trivial happening. At the second order, we have to allow for this possible shift in the SL2 quantum number, which is labeled by this J2. And once you plug this into the linear equation of motions, you actually obtain that J2 can be computed by computing this curly A. This curly A is actually nothing but the unshell 4-point amplitude, where two insertions are the zeroth order pulsating string vertex operators, and the other two insertions are the first order F3 vertex operator. And this is something that you can go and explicitly compute. It's 2D CFT computation. And this does not require level truncation or anything like that. It's literally just 2D CFT computation you can go and do, get the exact answer. And here are the answer. Okay? As you can see, I'm considering finite ADS radius here. This K is the W model level, which is finite. And I'm considering non-BPS spectrum. And we obtain very nice numbers. So if you previously thought that string field theory is a humongous conceptual formalism, which is very hard to use in practice, here's a counterexample. It produces numbers. And if you missed the entire talk so far, this is one takeaway message. Okay. Finally, let me come to the final example, flux compactification. So the question that we were trying to ask was very simple. Like, before going to any of the uplift or any of the story, can we actually do string perturbation theory in some flux compactification background? Okay. GKP presented the idea that one can use fluxes, D3, or planes, and so on to find type 2B Sugar solution with less SUSY and moduli stabilization. But due to the Raman fluxes, again, string observables in such backgrounds have been considered very tough to study, in particular string equation to the Kähler potential. And we can ask if string field theory may help. Let me give you some brief overview of GKP in somewhat simplified setup. So we are considering R1,3 times some Calabi-Oriented fold compactification, and we have 5-form flux, which respects the Poincare invariance of the 4D. We are also going to introduce 3-form fluxes, H3 and F3, which have components only along the compact direction. And we have D3 and O3s, which are space-time filling in the R1,3. And once you plug all of these ansatz into the type 2 Sugar equations of motions, these are the equations that you are going to end up with. First thing is something called ISD condition. You consider this G3, which is this combination of F3 and H3, and it should satisfy this thing. It's called imaginary self-dual condition. There are also Bianchi identities. In particular, for the 5-form, you have contribution not only coming from H3 wedge F3, but also coming from D3 and O3s. And there are further equations that one should satisfy. But let me make one point here. As you can see here, this G3 includes tau, axial dilaton. So there's string coupling explicitly arising here. So if you have order 1 quantized fluxes, this ISD condition actually requires the internal metric to be correlated with G string in some manner. This may be achieved by having some special choices of 3-form fluxes and large complex structure moduli, where perturbative 4D n equals 1 SUSY is simultaneously preserved. And if you wish an example, here's a simple example of that for the toroid-oriented fold. So Z corresponds to the complex coordinates for the torus, and UIs here are the complex structure moduli. We introduce this orbit folding, oriented folding, resulting in 64 O3s, and we are going to make this very specific choice of 3-form fluxes. You might ask why. At the string tree level, for the n equals 1 superpotential is given by the Gukov-Vapa-Witten expression, which obeys non-renormalization theorem. And once you plug the specific fluxes into this expression, you're going to end up with this quadratic expression. And then you can solve for the F-term equation, and you obtain one complex dimensional loci of solutions. And along this locus, the superpotential, perturbative superpotential vanishes exactly so that you actually have n equals 1 SUSY at least perturbatively. And by further investigating integrated Bianchi identity, you can conclude that the number of spacetime filling D3 should be 4. But notice that here, these complex structure moduli are now also associated with string coupling. So string perturbation theory, if it were to make any sense, should treat U inverse on the same footing as string coupling. So the question is now really, how do we do string perturbation theory in this case? Okay. We are going to start with open-close unoriented type 2B on this background with 4 D3s and 64 O3s. Okay. Because worldsheet CFT correlator on the torus part depends explicitly on the complex explicitly on the complex structure moduli. In order to systematically count them, we are going to introduce field line. So here, this psi I is the free fermion on the torus normalized to the internal metric, while this lambda I prime is normalized to canonical delta. So now the powers of G string are absorbed into these field lines. So for example, if you consider the B-field vertex operator and picture raise it, you are going to obtain this type of expression. And then for the explicit flux choice that I showed you before, this actually is of order G string to 1/2. And similarly, for the F3 vertex operator, you reach the same conclusion, is of order G string to 1/2. So you can say, okay, let's take this H3 and F3 as the leading order, G string to the 1/2 perturbative solution of string field theory, and let's subsequently build the higher order solutions. So this is now finding string field theory solution in mu, which is equal to G string to the 1/2 expansion. Okay, this is the first order solution. At the second order, this is mu squared, which is of the same order as G string. So disk and RP2 boundary states are also going to contribute. So that's the reason why this term is present in the equation. And after somewhat straightforward but a bit lengthy CFT exercise, you can find the solution. But you can ask, where are all these, ISD condition and integrated Bianchi identity and so on? Well, if you actually started with some generic choice of the complex structure moduli, H3 and F3, then the requirement that the equation has a solution actually leads to the expected integrated Bianchi identity and ISD conditions that we saw in the Sugar analysis. And you can also study the linear equations of motions at ghost number 1 in R, NS or NS, R sector. And they lead to the expected killing spinor equations, where non-trivial spinor solutions exist only if G3 is 2,1 form, so the perturbative superpotential vanishes exactly. So let me end with some discussions. Hopefully, I conveyed you the message that string field theory provides a systematic framework for studying interesting backgrounds, such as ADS and flux compactifications. And observables such as ADS Virasoro-Shapiro amplitude, which I believe is going to be discussed later in this conference from alternative viewpoint, and also string equation to Kähler potential in GKP, which I guess will be also mentioned sometime tomorrow in this conference, are now computable in string field theory. Okay? String field theory gives rise to first principle to compute these guys. Well, string field theory, if you notice, like so far I considered only the perturbative part of the story. Actually, string field theory can accommodate non-perturbative d-instanton contributions using the recently developed d-instanton perturbation theory. And I think I should mention that torus example that I presented for GKP is actually quite degenerate, because if you actually consider the Euclidean d-instanton contributions, they're actually comparable to the perturbative contributions because of this weird relation between complex structure moduli and G-string. So I would say that that torus case, which was just a toy example that we played around with, is actually a quite degenerate example. So the question is like the following: in GKP, whether there are Calabi-Yau's with large or small complex structure moduli, still allowing for suppressed d-instanton contribution is a very important question for flux compactification story. And I think it requires way more thorough investigation. And let me make this final remark. So in principle, string field theory knows how to deal with time-dependent backgrounds. You go and find time-dependent solution. An example which was studied intensively in the past is the open string rolling tachyon by Ashok Sen. And we can ask the question, can we address closed string cosmology? That's the end of my presentation, and thank you very much for your attention.
Thank you for an excellent talk. Are there questions? Yes, comrade.
Thanks for a nice talk. So if you start with a given background, which is given by a CFD, you beautifully describe how you start there and go ahead. But suppose you wanted to discover a background which is not near where you are. For example, start with 10-dimensional type 2 strings and you want to study it on a circle.
Oh, I see, circle.
Yeah, circle.
Good, good.
So that example already we know trivially how to do in CFD, but suppose you didn't know CFD and you just wanted to discover the winding modes. How would you discover it in string field theory?
Great question. So actually winding, I think, is something a bit more complicated than what I can describe now. So what I can describe to you is that at least you can consider some large radius expansion of the theory. But then actually talking about this winding mode will actually require you to talk about, if you have this, some local chart description, then how you can actually go beyond this. And I think the relevant thing is going to be mentioned in probably Shi's talk, because one now has to ask, what are the diffeomorphisms and so on in string field theory. And let me be frank, I think this description is actually not complete in the string field theory literature. So you're absolutely correct in that we currently have a hard time describing, for example, winding string, starting from the flat background.
Thank you. But it's not just the large radius limit. Like take, for example, T2 mod Z3.
T2 mod Z3.
Oh, sorry, R2 mod Z3.
R2
Just
mod
take
Z3.
a flat space and orbifold it. There's no state at infinity, but there are two-state sectors. That is not because of a large R limit or anything. You can't get that until you know how to treat that you're dealing with fundamental strings.
I completely agree. Yeah, I think, one of the things that current string field theory is missing is exactly about how to go away from this type of infinitesimal deformations.
Thank you.
Thank you.
Yes, Hiroshi.
So I would like to follow on this question about diffeomorphism invariance. So I think Kamara asked about, for example, compactification of circle. And so in that case, so if you consider circle, then you can actually cover the circle by several patches. Going from one patch to the other is still continuous deformation connected to the identity. So in principle, this is something one could do with the current technology, isn't it?
It's actually hard for me to answer this question. So let me tell you the following. So if you want to, for example, come up with some patch-by-patch type description, I think that's what you are referring to, then you actually have to consider strings extending beyond one possible patch, one patch. And I don't know how to do that. I think that's actually related to the current formulation of string field theory, which actually do not manifest covariance at any level. And I think it's one of the major challenges that current formulation of string field theory is indeed facing. But I think she will discuss some relevant issues in his talk.
Thank you.
Thank you.
Yeah, go ahead.
String field theory has promised an awful lot over the years, but again, I noticed in your presentation that when you unpacked it, you were essentially doing perturbative excitations around in supergravity. So what are the results that you can genuinely get that will go beyond supergravity perturbation theory?
I already presented it to you.
Aren't those simply conformal dimensions that you would compute by turning on a Ramon background and you could get this from the supergravity?
Not quite. So this is the fully non-BPS spectrum. And it's unprotected. And this is something that Suga cannot compute. And again, this is in the finite ADS radius. And I should tell you, this result actually is still yet to be reproduced from any other alternative formalisms. And we'll be very happy to hear about it from others.
So that looks a lot like Hamiltonian eigenvalues of the perturbations of the of the supergravity perturbations in the presence of background fields.
Well, as you can see here, we are considering this. This full string amplitude type expression for computing this.
Yes, go ahead.
Hi, thanks for the talk.
Thank you.
So you discussed that this can be useful to compute the alpha prime corrections to the Keller potential in these GKP n equals 1 backgrounds. It was not completely clear to me whether you have already computed some or the current technology allows to do so,
great.
or if there is a conceptual obstacle, or how far are we from doing that?
Great. So let me make two answers to that. So first is that if you want to really go and compute these things, you can, but it's just that we didn't do it. And these are very much like, you have this deformed background, and now you have to consider basically Kähler moduli, how they, what are their, like, say, 4-point amplitude on this deformed background, for example. So that's a computation which can be done in principle. But let me make another point, which is actually related to this very last slide. So this computation you can imagine doing in string perturbation theory. But again, there are actually d-instanton type contributions which are not necessarily suppressed for this type of weird, peculiar, like complex structure moduli and string coupling correlated manner. Okay. So I think conceptually, yes. I mean, if you just care about the perturbation theory and you have some trust in the perturbation theory, some orders, then you can go and compute these type of things. But I think this question is actually more important conceptual question which should be addressed more seriously. And I would say that this is a very difficult question. At this point, I actually do not know like any systematic way to pin down the Calabi-Yau where I can trust, say, first like few orders in perturbation theory without worrying about the non-perturbative contributions. But another point I wish to make is that these type of questions really start to arise as you now think about doing string theory on these backgrounds, rather than just go and find Sugar solution. Okay.
Yes, go ahead.
So in the ADS5 cross S5 example, how feasible is it to find the massive spectrum?
Great. So actually, ADS3 analog is exactly this one. Okay, yeah. That's the analog. Actually, all you need to consider, I would say that it's very feasible. All you need to consider is that you basically go and consider this mass 1 sector, so level 1 sector, and then you see how they actually develop the mass matrix due to the presence of the 5-point flux and the metric deformation. And then once you diagonalize it, you are going to get this spectrum. So for example, if you're interested in Konishi operator, you can do it.
So how come you haven't done it?
Good question. Maybe this is a great opportunity to invite whoever is interested. Yeah, I mean, as you can see, it's, yeah, it's unpublished. I mean, but let me tell you, we have all the ingredients. And we have all the ingredients to study massive spectrum and also ADS Virasoro-Shapiro amplitude. We have all the ingredients.
Any other question? You have a question? Go ahead, please.
So as you mentioned, unlike in the ADS3 case where you can perturb away from the pure NS background, ADS5 times perturbing from flat space to ADS5 times S5 would require a change of the asymptotics of the background. So how do you see this at the level of in your construction?
Well, all we see really is, this, as you can see in these solutions, we really see it only as a large radius perturbation. Okay? And as you can see here, like, okay, this metric, for example, the original metric, the full metric is like, 1 over r squared plus minus x squared and so on. And then we are basically expanding it like this. So I would say that this is the best we can see. But the important point is that we expect this to actually converge.
I guess one more example of this will come up in Z's talk probably, where you actually change the asymptotic background.
Yeah.
Asymptotics of the space-time. Yeah, go ahead.
Yeah, in ADS5 cross S5, if this is ever done, then you can compare with the known answer from integrability. Like, for example, Kanishi's scaling dimension is known as a function of coupling and some higher ones. So,
Indeed.
So in some sense, maybe this problem was already solved, but
I agree.
Would be great to compare with.
Indeed. And I wish to emphasize that this recent development on ADS Virasoro-Shapiro amplitude, which is supposedly containing more information than just first few, say, operators, is something that has only been done very recently, and now we have first principle way to compute them.
Sure. Yeah. Hi. Yeah. Sure.
Any other question? Yes.
Hi. Sure.
Yeah, go ahead, please. Yeah. Oh, I cannot see you, but you just go ahead. Yeah, okay, go ahead.
Can you imagine computing boundary terms like Gibbons-Hawking term or the ADM mass of a black hole or something like that in this?
Great question. Great question. So I think, so if you recall how Gibbons-Hawking York term was derived, it was basically requiring that you have well-defined variational principle in the presence of boundary. You can actually do similar exercise for string field theory. You have action, and then if you consider fields which do not necessarily vanish at the boundary, then actually you arrive at very similar looking term. But I think this has not been systematically studied in literature. And I think this is something that should be studied. Another relevant comment is that this is actually also related to the covariant phase space formalism that we heard several times here. There the story is very similar. You vary the action and basically get the boundary term, and then that gives rise to the symplectic potential, and then you can derive symplectic structure and so on. This thing actually has been studied very thoroughly back in the 1987, I guess, by Witten. And we recently revisited this in the case of open string field theory, and we were getting very nice physical observables using that. The case for closed string field theory is currently something that I guess Ted Euler is investigating. But I don't have much more thing to say than this.
Go ahead, please.
Thank you for the for the nice talk. Over the years, regarding the corrections to the Keller potential, people have computed corrections at different orders in alpha prime and in G string. Can you reproduce those already from the string field theory, and can you get some of them that haven't been missed?
Great. So in principle, yes. So it's not a computation that we did yet. We performed so far, but it's something that one can go and in principle compute. But again, I will make the same comment as what I made to Irene, which is that actually I think perturbation theory is nice, and string field theory provides you a framework to address them. But actually, to me, the real obstacle is just very big conceptual question that we should ask about this post-compactification is really whether one can have this well-defined perturbative series where the well-defined perturbative series where non-perturbative terms are indeed suppressed. And I think this is a very tough conceptual question. And I don't know the answer to this. Yeah.
Okay, yes, go ahead.
Hi, thank you for the talk. In GKP, as in other flux compactification background, you have this warp factor which captures the back reaction. And as you know, the back reaction close to the orientifold is problematic. And this becomes a crucial question nowadays in de Sitter or even anti-de Sitter solutions. So I was wondering whether string field theory has something to say about the region close to the orientifolds.
Oh, I see. Actually, I think you know something that I'm not quite familiar with. And I don't have much thing to say about that. But I will say that the problem is presumably not going to be resolved just because you are now considering string field theory. You're essentially going to see that your massless sector solution, not the massless, actually in this case it's massive because we are talking about torus, gives rise to exactly the Green's function that you obtain from solving this equation. And in our paper, we explain how you get this Green's function. And I think for that reason, we don't expect resolution of the issue that you mentioned.
Okay, I think in view of time, we'll just stop the discussion here, but there'll be more opportunity for discussion later. So we'll now move on to the review plus discussion session and hand it over to Ted and Z. Let's thank Minjae once more.